Right. Good morning. We stop. Before, let me check the audio first. Checking 1, 2, 3. Okay. Before we start to the, we continue from section 6.2 actually. Okay, it's good. I'll just go back to change a few things. Right. So this is on the first day. No, first day note. Let's make some correction real quick. By the way, if you have any question, just put on the chat, or you can always send me an email. And I got an email, so say that I make a mistake, which is not uncommon. Right. So you should go back to section 7.5, example. One D2, right. So once again, this is 7.5. 1D2. Right. So yeah, I'm here. I switch this to cotangent adjacent over opposite, well, which is correct, but I put it on the wrong place. Adjacent should be to x minus 5, and opposite should be 1. But when I put in the formula, cosecant is 1 over sine, and hypotenuse over opposite, so it is 1. So actually, the math is correct. I just got them switched up. Right. So that is section 7.5, example 1D2 that we did on the first day. The last example on the first day, actually. Right. So that's the first one. Yeah, we're talking about this one. Right. Next. Now this is more a typo. Section 6.1. Actually, we don't have any section 6.1. So all we need to do is, that is section 6.2. Actually, we don't have any 6.1. Right. Yeah, just change that. Right, so we're good. Right, and on Wednesday, we stop at this example. Where's this? I got, yeah, this example. And then bottom line is we can set the area based on dx or based on dy. Dx, it will be about, the region will be bounded by two functions, the one above minus the one below. If we set up using dy, it will be the one on the right minus the one on the left. So one of them is horizontally and one of them is vertically. Right, and we continue from that. today. And this one. Right. The example over there. A right. Sketch the region and find the area bounded by these two functions. Between cosine of x and sine x. Between x equal pi over 4 and x equal pi over 5 pi over 4. Right. So first, let's try to see the graph. Of course, we know the function sine, cosine, but let's graph both of them. Right. First of all, this is in terms of radian, so make sure the calculator is in the radian mode. So it is, which is good. Now we're just going to graph cosine of x and then sine of x. This should be easy, right? And then see the graph. Right. Maybe difficult to see, but we need to have pi over 4 to 5 pi over 4. So in that case, we might want to check the windows. Right. We know the sine cosine functions only between -1 and 1 on the y. So if we want to, we go down here, we check the y values first. Let's go from -2 to 2, because we know sine cosine between -1 and 1. The x-axis go pi over 4 to 5 pi over 4. So let's go from -pi and then go to 2 pi and see the graph. It will be better. Right? Even better if we want to, again, so this is -pi, second the hat, and then 2 pi. Right. In the scale here, we have pi over 4 and 5 pi over 4, so the increment is by pi over 4. So we can say pi over 4 as an increment. Now it will look a lot better. So this point here is -pi over 4. And this here is 1, 2, 3, 4, 5. I'm sorry, pi over 4 and 5 pi over 4. So we're talking about this here. Right, so let's draw a sketch real quick. pi over 4, 2 pi over 4, 3 pi over 4, 4 pi over 4, and 5 pi over 4. Right, the sine from 0 to pi so that is the sine, and then cosine will start from so we'll talk about that. Right, so that is sine x, and and the area is going to be between pi over 4 and 5 pi over 4. So we're talking about this area. Right. So let's take a look. So we try either dx or dy, and on this one obviously it's going to be dx because we have two functions of x in that look. So we take pi over 4 and 5 pi over 4. So this is the region. We see that the function, the region is bounded above by the red function, which is sine x above, and below is cosine x. So pretty much just the function above subtract the function below. And the limits pi over 4 to 5 pi over 4. Right. Okay. Now let's find the area. So we actually do the integral here. Right. Integral of sine is negative cosine. And integral of cosine is sine. So pretty much that's what we have. And this integral going pi over 4 to 5 pi over 4. Right. And we just put pi over 4 and pi over 5 pi over 4 and pi over 4 into it. So negative cosine of 5 pi over 4 minus sine of 5 pi over 4, and then we're going to put pi over 4 into it. Right. Cosine pi 5 pi over 4. So that is second quadrant. So negative square root 2 over 2. And sine 5 pi over 4. Square root 2 over 2. Yeah, we can just look at this. Wait, 5 pi over 4, that's also negative. Yeah. And then subtract. Negative cosine pi over 4. Square root 2 over 2, which is about this. And minus sine square root 2 over 2 as well. So when we remove the parentheses, all the positive and all the negatives, square root 2 over 2 plus square root 2 over 2 plus square root 2 over 2 and square root 2 over 2. So when we add all of them up, there are 4 of these. So let's check real quick. Pi over 4 to 5 pi over 4 sine minus cosine, oops, right, and then 2, yeah. So of course the calculator cannot give you that answer, but that is equivalent to it. Right, so that's the first example. Right, next. Now the region is bounded by these two functions, y equal to a minus 2x, y equal to x plus 8, and y equal to 0. Right, sorry, one thing I forgot. Last time, if you want to second hit the window key, that give us, second the zoom. Now we're going to turn the grid on, so the graph will look better with on the grid. Now first, let's sketch this function. Y equal to a minus 2x and y equal to x plus 8. That's good. And y equal to 0 is the x-axis. Right, let's see the graph. Right, just a reminder, the video that I'm streaming is in 1080p, so make sure to change the resolution to 1080p, also it will be clear. Right, so of course that's not what we see, so we have to go back to the standard windows. So zoom number 6, that is the standard windows. Right, so and the standard windows go from negative 10 to 10 on the x-axis and the y-axis as well. Right, so that's what we have. Going to be the big graph. Oh, just fit the page. Right, so 2, 4, 6, 8. Right. First, let's look at this graph. That is the linear function, so this will be easy. Choose some value for x. When x equal to 0, y equal to 8. When x equal to 1, y equal to 6. X equal to 0 is 8. When x equal to 1, to 6. So we have this. Right? And then next we have the y equal to x plus 8. X equal to 0, y equal to 8, x equal to 1, y equal to 9, but that's not, it's not on the screen, so choose something else, like negative 2, it's going to be 6. And we see both of them have the same point of 0 and 8. Right. So there's an intersection. So it's just this triangle. Right? Now, let's set up the integral first. Wait, let me just write the function y equal to x plus 8. So we're talking about this area here. Right. So when we look at this, if we talk about dx, meaning the function above minus the function below, above it is bounded by this function, and below it is bounded by the x-axis. By the way, y equal to 0 is the x-axis. So this we're talking about the triangle here. So again, if we're going to use dx, it's going to be 1, 2 boundary. So there's inconsistency there. If we want to set up dx, we have to split the limit from 0 to 8, negative 8 to 0, and then from 0 to 4. So quickly, if I want to use dx, we have to go from negative 8 to 0. Have to do that first. So the boundary on the top is x plus 8 minus the bottom 0. And then over here from 0 to 4, the graph bounded above by a minus 2x and the bottom 0. From 0 to 4, it is bounded above by x plus 8 8 minus 2x. And the bottom 0. Yeah. So if we set up using dx, we have to split into integrals because we have two boundaries above. Now, however, if we set up the integral using dy, it is bounded up on the left by this function and on the right by that function. So if we use dy, it will be just one integral. And that integral, in terms of dy, the y values go from 0 to 8. So we know the limit. Now we just need to know what is the function on the left, what is the function on the right. Notice that since we use dy, everything in here has to be in terms of y. So equivalently, y equal to x plus 8, we can say x is equal to y minus 8. And that is the function on the left. The function on the right, if we solve for x, move the 2x over and y minus 8. So 2x equal to a minus y, or x equal to, divide by 2, 4 minus y over 2. So we're talking about this function and this function. Right, so dy, we look sideways, the function on the left to the function to the right. And as always, the one on the right minus the one on the left. The bigger function minus the smaller function. So we start with 4 minus y over 2. And then subtract the function on the left, y minus 8. Right? So, because on this problem, the limit on we using the left and the right. There's one on the left, one on the right. So we only have one integral. If we're talking about up and down or above and below, there's one function below, yes, but two functions above. So we have to have two integrals. So if we have more than one boundary, then we have more than one integrals. Right, by the way, if we just want to find the area here, we don't even need any integral. It's just area is 1/2 base times height. The base is from -8 to 4, so that is 12. And the height is 8. So either of those, both of those integrals should give us 48. No, the reason we know the bigger function is it is on the right. No, I'm talking about the x or the y values. I assume that you're talking about the y values. The reason we know this one is the bigger function because that is on the right. Just like on the x-axis, the bigger values on the right, the smaller values on the left. So the bigger function minus the smaller function. It's always like that. The bigger function minus the smaller function. Because after all, we're trying to find the area. Area cannot be negative. So the bigger number minus the smaller number. The function above minus the function below. The function on the right minus the function on the left. Right. We have a lot more example here. Right. B. Now this one will only sketch and set up the integral. And with respect to x, with respect to x, and with respect to y. For the region bounded by y equal to e to the x, y equal to 1, and x equal to 2. Right. So first I'm going to graph this function, see what happened. So y equal to e to the x. Second, ln e to the x. Y equal to 1. 1. And x equal to 2. That one we kind of have to imagine. We won't be able to graph x equal to. Alright, so that exponential function e to the x and y equal to 1. So kind of difficult to see. So I'm going to zoom, hit zoom. The first one, zoom box. So I'm going to zoom out. Zoom in. Actually, yeah. So I have to go from x equal to 2, so around here. So let's look at the graph. Right? And y x equal to 2 is that vertical line. So we're talking about this kind of shape. Right. Right. By the way, let's find out real quick. We have e to the x. When x equal to 2, pretty much we have e square. Sorry. E square is about 7.8. One, 2, 1, 3, 5, 7.3. So that's about there. Right. So let's find out real quick. So first, if we want to, let's sketch the function, exponential function. By the way, this is with respect to x. Let's just do that with respect to x. Right, just make a table y e to the x. So we have x. When x equal to 0, y e to the 0 power is 1. X equal to 1, e to the first power is e. Wednesday, find out that is 2.71828. And when x equal to 2, we just did 7.4. So here, here, and here. Yeah. Exponential function, it will grow rapidly to infinity. Right. Next, y equal to 1. Well, that one easy. Just a horizontal line. and then x equal to 2. That is the vertical line at 2. I'm going to do this example very slow because this is essentially very important in calculus 2 and calculus 3 as well. So we have to be able to set up the limit. Alright, with respect to x. So the limit with respect to x. Right? And with respect to x, when we look at this, by the way, 1, 2, and 3. So we're talking about this area here, right? Talking about this area. And with that, the limit, the x limit is going from 0 to 2. Let's go back to the graph. I'll go from 0 to 2. Obviously, that's the limit for x. Because we have dx, we write the limit for x. So the limit usually easy to determine, especially when we have the graph. Right? Now, if it is dx, it's going to be the function above minus the function below. Let me write this. If it is dx, it's going to be the function above minus the function below. And then the limits, right? So the function above is obviously y equal to e to the x. So it has to be a function of x. So that's easy. That is the function above. Minus the function below. So above is bounded by that curve, and below is bounded by this line, right? Y equal to 1. So just minus 1. And it's a constant, which is perfectly fine. We cannot just put y in here. If it is dx, everything in here has to be x. So just like that. That's easy. Now I'm going to do the same thing, but with respect to y. So I'm going to draw that graph again. Seven. Right. So if it is dx, function above minus the function below. The reason of that is, remember, if we have dx, so it's very small here. So that is a dx, right? A very small increment of x. So we're talking about this region here. And that little rectangle, the width is dx, the height is the difference of the two functions. So we need to find the area of one rectangle. Therefore, the width is dx, the height is bounded by those two functions. One above minus the one below. Give us the height of that rectangle. Right. Now I'm going to draw that graph again. Y equal to e to the x, y equal to 1, and then x equal to 2. This one is with respect to y. Now with respect to y, we talk about this region, of course. It is going to be the function on the right. minus the function on the left in terms of dy. The limit is easy to determine. So the reason we do that is when we're talking about dy, it's going to be this little increment, right? And so we're going to have the little rectangle where the height is going to be dy, and we need to find that distance, which is the function on the right minus the function on the left, to find the area of one thin rectangle. The height is dy and the width is going to be the right minus the left. So that's why for dy it's one direction, and then we have to find the other direction perpendicular to it, and that is from the right minus the left. Right, so pretty much we have a bunch of those rectangles. So now the limit is going to be dy, the function on the right minus the function on the left. Right, now if we look like this, the function on the right is the line x equal to 2, so that's easy. For some reason I just switched color for no reason, so this will be in blue. So the function on the right is 2. Subtract. The function on the left is e to the x, right? Y equal to e to the x. I could not put e to the x here because that's a big problem. It is dy. Everything has to be in terms of y. We cannot put x in here, right? So if y equal to e to the x, then how do we solve for x? So we have to take ln on both sides, right? ln and e cancel out. We have y on the right for that. Y equal to ln. I'm sorry. When we do that, x equal to ln of y. Exponential function and logarithmic function are inverse of each other. So x is equal to ln of y is equivalent to y equal to e to the x. So if we want to, the function is ln of y. So function on the right minus the function on the left. Now the limits. The limit in terms of y. This region we're talking about from 1 to the lower limit is easy. And what will be that upper limit? Since we have the function y equal to e to the x, when x equal to 2, y equal to e squared. So we have the point here, 2 and e squared. So the limit for y is going to be from 1 to e squared. Right. So it is very important that we know how to do this easily. I mean comfortably set up the limit for x and the limit for y. And if we do the integral of those two, should come up with the same result. Right. Next. C. Example 3. A sketch and set up integral. With respect to x and with respect to y for the region y equal to x squared, y equal to x plus 2. Now this may be complicated, even though the function seems simple. Alright, let's see the graph first. Y equal to x squared and y equal to x plus 2. Right. Let's get to the right scale then. Zoom number 6. Right, so look like that region. Right, zoom box. Right, much better then. Right, I have the request to have the whole prompt again. So that is with respect to x, a function above minus a function below to give us the height, and then the dx is the width. We have the area. And if it is with respect to y, meaning we use dy, the function on the right minus the function on the left give us the width, and the height is dy. So we have one rectangle. So always have to have the area of rectangles, and when we add all of them up, we have the whole area. So that's why we have that. Right. Now to get the region integral, so that's easy. Y equal to x squared. Right. By the way, on the intersection, we look like the intersection is going to be negative 1 and 1, and when x equal to 2, y equal to 2 and 4. Right. So simple enough. Now let's first we do with respect to x. Y equal to x squared x equal to negative 1, y equal to 1, 0, 0, 1, 1, and then 2, 4. So just have some point. Right, and then the other one, y equal to x plus 2. Right. X equal to 0, y equal to 2. x equal to 2, y equal to 4, right? So there's the intersection here. And we can see there's an intersection here of -1 and 1, and then 2 and 4. Right, so in this integral we will set up the limit using dx, and then we're going to do the same thing for dy. Right, so dx it is so dx is the width. We're going to need the height, so we have the rectangle, right? And adding all of this rectangle, get the area of the whole region. So we talk about that one. So the function above minus the function below. On the top it is bounded by y equal to x plus 2, and the bottom is bounded by y equal to x squared. So there is a consistent between the function, one on above, one at below. So one on the top, one at the bottom. So we only need one integral because there's only one boundary on each side. And in terms of the limit for x, it goes from -1 to 2. And then the function above, x plus 2 minus the function below, minus the function below, x squared. Right. So that's simple. That's the limit with respect to x. Now we will do the same thing, but with respect to y. So pretty much I draw the same region. 2 before the point 2 and 4, then 1 and 1. Right. So now this one with respect to y, meaning we use dy, right? So if we use dy, it's going to be the region on the right minus the region on the left. So now this one's tricky. If we look at it, on the left, it is bounded by this function and this function, right? There are two functions. In particular, I have to split here. This region bounded from the left and then bounded from the right. Now for that one, from the left and on the right. Right. So because of we have two limits on the left hand side, we have to use two integrals. When we have more than one limit, have to be more than one integral. So we're going to set up two integrals. One of them, let's just do integral first. Right, so there will be two integrals because there are two boundaries on the left hand side. Right, now, so if we look at that, on the left bounded by y equal to x squared, on the right also y equal to x squared. So how do we do that? But for the first region, it is from 0 to 1 for the y. From 0 to 1, so we're talking about this one. On the left, by y equal to x squared, on the right, also y equal to x squared. But remember, when we put the limit here, it has to be in terms of y, right? So when y equal to x squared, if we want to solve for x, we're going to take the square root on both sides, right? But whenever we do that, we have to put the plus or minus on one side. So we have square root of y equal to plus or minus so we have that. Or of course you can put the plus or minus on the left hand side. So x is equal plus or minus square root of y. Indeed we do have it on this side. That one, we have x equal to negative square root of y. And on this side, y equal to square root of y positive. I mean x equal to square root of y positive. So in here, the function on the right is square root of y, has to be a function of y, and subtract the function on the left, also the function of y, square root of y, negative square root of y. So that's what we have for that integral. Right, next, we're talking about the integral on the top here. The function on the right is easy. It's going to be square root of y. The function on the left is y equal to x plus 2. It's not as bad. Y equal to x plus 2. So x is equal to y minus 2. When we use dy, it has to be function of y. It could be constant, but cannot be x in here if we use dy. By the way, the limits is going to be from 1 to 4. Talking about this one. Right. So See if I can zoom this in. That's still good, right? Yeah. Now we go from -1 to 1. Because, first of all, if y equal to x squared, then x equal to plus or minus square root of y, right? So, we have on the left hand side here, is x equal to negative square root of y. And on the right hand side is x equal to positive square root of y. Right? So even though it's come from y equal to x squared, it's not a one-to-one function. That when we split up into x, it will be negative square root of y and positive square root of y. Now, on this region from 0 to 1 on the y, it is bounded on the left by negative square root of y and bounded on the right by y equal x equal to square root of y. So, it's always the function on the right minus the function on the left. The right function is positive square root of y and the function on the left is negative square root of y. So for that region here, it is bounded by those two functions. And then for the one on the top, from 1 to 3, from 1 to 4, on the right is still the positive square root of y, and on the left it's going to be y minus 2. Right? Yeah, before we go to the next section, I just want to do this pretty quick. So, let's do this summary, maybe it helps. If we're talking about dx, of course the x-axis is horizontal, right? This has to be the function of above minus the function below. You mean we don't use x squared here? Oh, we don't use x squared here because that has to be a function of y. So that's why we have to convert everything into term of y. And when we convert y equal to x squared into x, into the function of y, this is plus or minus. So we know it's going to be 2 function in term of y. And we don't use the y equal to x plus 2 because it's not there from 0 to 1. We don't see the left function other than just the curve here. Right. So on the summary, if we use dx, we need the function above minus the function below. When we subtract those two, give us the height. The height and the width of the dx can give us the area of a rectangle. We always need to have the area of rectangles. Add all of them up, give us the area of the whole region. Now if we draw the horizontal rectangles, that will be dy, right? dy is vertical. We're going to need the function on the right minus the function on the left. And we have to subtract those two. So give us the width along with the height. The dy, we know the height. We still need the width. As always, the right minus the left. The difference of those two give us this length times the dy give us the area of the rectangles. So whether we have a horizontal rectangles or the vertical rectangles, we need to have the other sides perpendicular to it. If we use dx, the perpendicular to it is above and below. If we use dy, the perpendicular to it is going to be left and right. I think maybe that helps. And we're going to need to use this for the remaining chapters. And well into calculus 3, we have to use a lot of this. So that's why I go a little bit carefully in this section though. Right, let's take 5-minute break. We continue at 9:13. After that, we'll go to section 6.3. Yes, the x equal to y minus 2 on here, that is the limit on the left. Yes, but for the one below, we don't have that on the left. The one below is negative square root of y. Yeah, since there are two boundaries on the left, that's why we have to split the limit in two. Yeah. So when there's more than one limit, more than one boundary on one side, we have to cut that in two. So will be left and right, left and right. Yeah. The previous example, we don't have to do that because we have one boundary on each side, so we only need one integral. Yeah, it's a little bit more difficult when we have to split the limits, where we have to have more than one boundaries. Right. We certainly will need this to go to the next section. Right. Section 6.3, volume by slicing. So this will be tough to do, especially this is 3D. So try to see if we can zoom in. Alright, so imagine we want to take the area of this region here. I think we can do that. So we're trying to find the area of that. Oh, it's not that bad. Can we zoom in? Right, much better. So we're trying to find the area of that, of the whole thing. So in that case, if we want to find the area of the whole thing, so we just chop it or slice it into slice. And so the volume of the whole thing, this section we find the volume. So the volume of the whole thing equal to the sums of the volumes of all of the little bit of this. So that's like a slide of sandwich, for example. Slice bread. Right? So in order to find the volume of one piece, it is going to be, since we're going to slide that, I assume that's going to be unit with on the slide of the whole bread of the same width. Those width is either dx or dy. So we're going to have dx or dy, kind of like what we did previous section. And then once we have the width of one slide, we have to find the area of the cross-sectional area, right? And with that, we have the formula of the width times the cross-sectional area, and that, right? So how do we put on the note? Kind of difficult. I try to draw with pencil here. Let's draw something like a shadow. I mean. Recommend to do that with pencil. much better than I thought. So we have this region here. Right, and then we take one slice, so we chop that into slice. So I'm going to take one slice, so that is one slice. If we can find the volume of this one slice and add all of them up, we have the volume of the whole thing, right? And this line we have the width of a slide. Yeah, so this is more of a slide. So we're going to cut a slide, and we have the very thin, the width of a slide. In this case, let's just for simplicity, we use dx. So the width here is dx. And then we're going to knit the cross-section area. That is the cross-section area. Because after all, if we knit the integral of dx, it has to be the function of x. Right. So cross-sectional area times the width gives us the volume of one slide. So the volume of one slide is the cross-sectional area times the width. And the volume of the whole thing will be the sum of all of those slices. So this is the volume by slicing. Once again, dx, the width, and then the area of a cross-sectional area. Cross-section area. So let's go to the first example. A solid has the base bounded by y equal to x squared and y equal to 2 minus x squared in the xy plane. Cross-section are perpendicular to to the x-axis and all similar semicircular discs. Find the bottom. Right. So this is a three-dimensional problem. So we have to turn the x-axis sideways. So on this graph, the x-axis is here and the y-axis is there. I'm not sure if I can draw this well enough here, but I will try it. So x-axis and the y-axis. And we have one function and then the other function. It is terrible. And then the other function. Again, this is the y-axis. And the x-axis is horizontal. Right. So we have like that. And then the region we're talking about is the one that is so it's much better on the graph on that side. Right. By the way, when we actually do the problem in this section, this is not this complicated. At least it will be a lot easier to visualize. So now if we only talk about the XY plane, y equal to x squared and y equal to 2 minus x. Oops. To my x squared, and we're talking about this region. Right, so we're talking about that region on the XY plane. Now what we're trying to do is imagine there's the semicircular that go above like this, but each of the width, each of that will form by a semicircular disc. So we're going to put a disc on the top of it where the base is the diameters. So first we're going to set up this is going to be the diameter of the semicircular, which go up and down. So that will be like this. So it's kind of difficult to see that the graph there is actually is the best we can come up with. Right, so this is the diameter, the function above minus the function below give us x squared minus 2 plus x squared equal to 2x squared minus 2. And if we divide everything by 2, give us the radius. So that is the radius of that semicircle. So we're just going to stack this on top of it. So it's like this. I'm trying to zoom it up. So this is kind of semicircular on the top of it. Right. And then the volume will be from -1 to 1 because we use dx. And the area, cross-sectional area, this is the semicircular disk, so 1/2 of the whole disk. One half. The radius is this one square and dx. So when we do that, we have the volume. Why nobody say anything? Right, let's do that again. Because it's not right. Diameter again. The function above. That's why all the color code is for the function above minus the function below. And with that, the radius is 1 minus x squared. Sorry. I have this. Yeah, it's just from the last section we have to know that the function on the above minus the function below. Sorry. Right, and so that is 1 minus x squared. Right. Right. So we don't have to do too much of this. What we have is we assume that all the volume now is going to be the whole disk. It's not going to be semicircular or pyramid or anything. Right. So this method this method, what we're going to have now is going to be a whole disk, like I said. It's not going to be a semi. With this one. Yeah, sorry. like I said, the diameter is going to be the one above minus the one below. So the above 2 minus x squared and below is y equal to 2 minus x. So basically we're going to have a disk, a semicircular disk, kind of, and the diameter is going to be below here. So we're talking about that here. Right. Right. This method. Now, it will be a lot easier on this method here. So let's just try to draw a region here. Now for this we actually can draw for real. Right, let's see, we have the graph. Right, the function goes like that. And we only interested in the region from A to B. So, like I said, the last problem, it's just the introduction. We're not going to worry much about that. Right, let's say we have this region. I'm not going to mark everything to it, so that is light region. Now imagine we're going to have that, and we rotate around the x-axis. So now we rotate around the x-axis. Clockwise or counterclockwise, doesn't matter, but we rotate around the x-axis. So you see on the graph on that side, if we have the region R rotate around the x-axis, we're going to have that kind of more like a bullet shape. So if we rotate, it will be kind of because we cannot really see on the back of it. So kind of. So that's the best I can see. So we're talking about the bullet shape. Right. Now for this one, of course, we do the same thing. We're going to slide that into slice, and we're going to use dx. Right. Now I'm going to take one slice of this. And I'm going to put on this side. So we have one slice. So we would take one slide of it. It will be like that. The perspective make this one horrible. Anyway, so we take one slide, and then the width here is going to be dx, and then we still have the function as the radius is the function, and the cross section is just the area of a disk. So cross section area is just going to be the disk. The radius is f of x, so pi f of x squared, and put that all together. The volume equal to the area of cross section square times dx, the width, and from A to B. Right. Here's we have a note. This method for dx, that is the formula. So in general, we're going to have the integral, some limit here. It's going to be pi r, which is the radius, square, and then times the width. In particular, on this case, we're going to have pi r square, and then we can use dx. In the next part of the section, we could use dy too. But if it is x, the function have to be in terms of x. If it is y, or later we're going to use pi r square and dy. We could do that too, but the width here is either dx or dy, and r is the radius, have to be function of x or function of y. Right, go to the first example. So part r square, this part of part r square here is the cross-sectional area. Example 1. Let R be the region bounded by x plus 1 square the x-axis x equal to -1 and x equal to 1. Find the volume of the solid of revolution obtained by, I'm going to have to write the whole thing out, by revolving about the x-axis. Right, so the first part is just like in the last section, we try to draw the region R. So we just have x plus 1 square the x-axis is y equal to 0, so we're just going to graph that. So try to draw R. Right. X plus 1 square. Originally we have x square, and x plus 1 square plus 1 it go to the left. I'm not going to move this because it look backward on my screen, so it's kind of off. So but that will move 1 unit to the left, meaning that we have the parabola like that. Negative 1, 1. Right. If we want the table, I should have done this earlier. Second graph, give us the table. Negative 1, it's going to be 0, 0 is going to be 1, and 1 is going to be 2. 1 is going to be 4, sorry. Yeah, I should at least show that at some point. Right. And this region is bounded by the curve and the x-axis y equal to 0, and then also from negative 1 to 1. So this is the region R. Right. Now what we do is we're going to rotate this about the x-axis. So we're going to turn this region and we're going to rotate that about the x-axis. So if we rotate that, it looks something like this. And then this is I'm not sure what it looked like. It looked like a cone, but it's not straight. It kind of bended. Right. Now, what we're going to do is the volume here is going to be by this method. So the volume is going to be equal to pi the radius square, that is the cross-sectional area, and then dx or dy. By the way, if it rotates about the x-axis, it's going to rotate like this horizontally, and if we're going to slide it, we're going to chop it we're going to chop the x-axis. Therefore, it's going to be the same as x-axis. So this method, if it is the x-axis, we're going to cut the x-axis. Therefore, it's going to be dx. It will be easy also from -1 to 1. So that's easy to determine. Now, the only problem in this method is to determine what is the radius. Before I go to that, let's go back to this formula. We can always pull out the pi. We can always pull out the pi. Right. It doesn't matter though. What matters here is how do we find the radius. Now, what is the radius? So now we have that region and we rotate about the x-axis. So the radius is pretty much from the axis of rotation go out to the edge of the region. Or just like when we find the areas of the radius of a circle. So when we have a circle, the radius is from the center to the edge of the region, right? Same thing here. The axis of rotation. So the radius will be from the axis of rotation, the x-axis, and this is going to be on the edge of the region. So we're talking about this one here. That is the radius. From the axis of rotation. So when we rotate, that part rotates. And so that is the radius. Now to set up the radius, it's just like what we did earlier with the function above minus the function below. On this one, it's going to be above by x plus 1 square. Below, it's just going to be 0. So that is the radius. And put them all together. So the volume from -1 to 1 pi x plus 1 square, that's the radius, and then we have to square again because we need the radius square dx. Right. I can pull out the pi from -1 to 1, and then we have x plus 1 square, and then square, multiply those two together to the 4th power dx. That's what we have. Now if we just use the calculator to evaluate this integral, leave the pi out of it, and math, and then we just do the integral -1 to 1 x plus 1 to the 4th power convert to fraction 32 over 5 and then at the end stick a pi to it. So if we use the calculator, leave the pi out, do the integral first, and then put the pi back in. Right. So it's very easy in the component of this method. In this case, if it is dx, we rotate around the x-axis. Just need to determine the radius, which is the distance from the center of rotation, the axis of rotation, to the edge of the region. So that is that. Right. To the next example. Next one, set up the integral to calculate the volume. Now we just want to set up. Alright, let's see the graph first. Y equal to square root of x minus 1. To just pretty much square root of x. It's like the curve. And then move 1 unit to the right. Right? Let's see the table. Right, when x equal to 5, y equal to 2, x equal to 1, 0, x equal to 2, 1. Yeah. Right, and from 2 to 5. So this is kind of like the bullet that we have earlier, and we will rotate about the x-axis. And this is the region R. Talk about this region R. So if we rotate, we don't even have to draw it, but it's kind of like a bullet. Kind of like that. Right. Now, the volume of the disk, since this is rotating about the x-axis, it is going to be dx. If it rotates about the y-axis later on, it's going to be dy. So pi r squared. Pretty simple. Now, the x, the limit for x, 2 to 5, that also easy to determine. The only thing, we need to determine is what is the radius. So the radius, it is counted from the axis of rotation on the edge of the region. So that is the radius, capital R. And then we just do like we did before, the function above minus the function below. Pretty much just that. Minus 0 if you will, it doesn't matter. Just that. And that will be equal to, I'm going to put a pi outside. And the radius is square root of x minus 1. And we need to square that. And so when we do it, we have pi integral from 2 to 5. Square and square root cancel out, just x minus 1. So that's simple enough. Right. I should integrate this, but so that's 15.5. I'm sorry, 7.5, 7.5, meaning 15 over 2. That integral, and we stick a pi to it. So pretty much that. So under this method, if it is rotated about the x-axis, that's going to be dx, easy. Determine the limit for x, also easy. Pi, and then the radius square. Only need to determine what is the radius square, or what is the radius, and then we square it. That's pretty much it on this method. Next we'll go to the washer method. Well, let's take 5-minute break. We'll continue at 10:06. So we continue with the washer method. Once we get to this method, it should be easy. Once again, this method, dx, part r square, and just need to determine the radius. By the way, I realized that in here we use r as the region too, but for now we just use the region r as the script. I'll do change that in the next round. Next, the washer method. First of all, when we talk about washer, we're not talking about the washer like in the washing machine. We're talking a washer is kind of thing where we put in the bowl. Washer is it's not a donut, but it's have a hole in it. And usually a washer is the one that we put around a bowl so that we not tie it up. So do I have that? Anyway, so go to the graph. So pretty much what we have now is just do the sketch. See, we have one function above. And the function below. See, from A to B. And we're going to rotate that also about the x-axis. So when we rotate, the outside will rotate and the inside also rotate. And so we're going to have that, and then on the outside it's much better than I thought. So pretty much what we have is just like the region, but we have the hollow region. The hollow region is given by that. Right. So in that case, the washer method, if we rotate about the x-axis, it's going to be dx. The x-axis rotating around it, and when we chop in the axis of rotation, so it's going to be dx. Integral for x from A to B. Excuse me. Right, from A to B. Right, so Now to find this area, I mean the volume, it's going to be the big volume, the whole thing, and then we just take away what inside as the hollow region. So the big volume is going to be pi r squared. The big radius minus the little volume. This will be red. And then minus the hollow region, pi r squared. I use little r. So, and then if we factor out the pi, we're going to have the big radius square minus, thank you, the little radius square. Right, so we have the whole thing and then take out the hollow region in the middle. That's pretty much it. The reason I don't want to write this is f of x or g of x, like what we have in the note, like what we have here, because in general it's better the way we define that without the x or the y values in the formula. So again, the volume, we can put the pi inside or outside of the integral, it doesn't matter. I guess put inside. And we can write like this too. The big radius in terms of x square minus the little radius in terms of x square dx. Yeah, let's just write like that. Yeah. So when we write the big radius and the little radius, we don't have to worry about what function is bigger than the other function. Just the big radius square minus the little radius square with a common factor of pi. So bottom line, it's not that big of a deal. So we have the whole volume by this method minus the hollow region by this method. Subtract those two, be like this. And we don't even need to write the note. But let's just do that. Right, the washer method, if it is just like this method, if it is rotate about the x-axis, it's going to be dx, and r is the big radius, or I should say the outer radius, and little r is a small or the inner radius. And pretty much that. So as far the formula goes, it's pretty simple. For this one, we just have the two radius, the big one, the outer radius, and the inner radius. And the radius is from the axis of rotation to the edge. Right. See. The region R. Now for the region R, I'm going to write the script R. Is bounded by f of x equal to square root of x, and g of x by x squared between 0 and 1. Find the volume of the solid when we rotate the region or about the x-axis. Right. First we have to sketch the region script R. So let's see. Pretty much x squared and square root of x, pretty simple. Right. It's only from 0 to 1. Square root of x and then x squared. And we rotate about the x-axis. So for this washer method, this is going to be the washer because we will see why. But this is about the x-axis, so it's going to be dx. And this is the region R. Script R. So the limit obviously from 0 to 1. So it's easy. Determine dx or dy is easy. And then from the limit should be also easy. Now what we need is just the big radius square minus the little radius square. Just need to determine what is the big radius. So the big radius is from the axis of rotation from the x-axis to the edge. So we go from the axis of rotation to the edge. So that is the big radius. From 0 to square root of x. Right? Next, the little radius also from the axis of rotation, the x-axis, go to the edge. And so this is little r. which is the function above is x squared minus 0, so just x squared. Right, so put everything in the integral. So to 1 pi. The pi can be inside or outside. Something square minus something square dx. The big radius is square root of x. Small radius x squared. Right. So this one is simple enough. I'm going to do that by hand. Square root of x squared, so that's just x, and x squared square again, x to the 4th. Can take the pi outside. So we have x minus x to the 4th dx. Alright, I will not involve the pi in any calculation until the end. So integral of x to the first is x squared over 2. Integral of x to the 4th, x to the 5th over 5. Integral from 0 to 1. Now we're going to put 1 into it. And then subtract when we put 0 into it. This will be equal to pi 1/2 minus 1/5. 0 and 0, so this goes to 0. So that's just 1/2 minus 1/5, which is 3 over 10. Or the answer 3 pi over 10. Right. I'll check real quick. Even though if we use the calculator, do not put pi into it. Just do the integral from 0 to 1. No. I'm not talking the f of x or r, the g of x is g. It doesn't matter. We don't know that. Just the big radius is from the center to the edge. Which one is bigger is big R. Which one is smaller is the little r. So it might not be f of x or g of x. Depends on the function. So that's why I just write the big R and little r. It could be something else. It could get very complicated later, but for now it's not as bad. Yeah, so 0.3, which is 3 over 10. So to recap, on the washer method, we only need to determine the important here is what is the big radius and what is the little radius. The big radius, of course, is the bigger one from the axis of rotation to the outer edge. And the little r is from the axis of rotation to the inner edge. When we rotate, we have the graph of that. It's like what we have here. So the big R is from the axis rotation to the bigger function. The outer function it's not the bigger function, it's the outer function, because potentially we may have the region that go like this. In that case, the big radius go to the outer function and the little radius go to the inner function. So it's not always f of x and g of x. It will not be straightforward like that. It could be a lot more complicated. So that's why we have to draw it out and see from the axis of rotation which one is outer, which one is inner. Right. Onward, we have a lot more example of this. Especially when the axis of rotation is not the x-axis or the y-axis. That's where things get complicated. The region R is bounded by I'm just going to say y equal to 2x. So, and g of x. And then y equal to x. I'm not going to write f and g because it's not always f of x, it's r and g of x is little r. We always have to draw it out and see what happens. Sorry. That's why I'm looking for. Right, that's better. Right, as always, first we're gonna sketch the region R. 2x and x, so that should be easy. 2x and then just x. Right, that is 2x and this is x. Right. Right. Y equal to 2x. That easy when x equal to 0, y equal to 0, x equal to 1, y equal to 2. So that is y equal to 2x, and now y equal to x. That's easy. Don't even need the table. When x equal to 1, y equal to 1, and x equal to 0, y equal to 0. So those two. From x equal to 0, meaning we go from here and to 2. And this one also revolving about the x-axis. So this is going to be dx. And here we have the region R. Rotate about the x-axis. Right. So now after we draw a bunch of them, let me go back to the one with the disk. See, the one with the disk, it will lie on the edge of the axis of rotation, so there's no hollow region. So the one with the disk method, there's no hollow region because the edge of the region R is the axis of rotation as well. Now here, the axis of rotation is the x-axis. When we rotate, of course, there will be the hollow region here. And when we rotate the inner, so the big radius, we generate the big cone, a cone. Both of these are cone, and so we have to take out the region in the middle. So because there is the hollow region, it's going to be big R square minus little r square, and we use dx. And the limit for x, obviously the region here, the limit for x goes from 0 to 2. Now we just need to determine the big R. The big radius is from the axis of rotation go to the outer edge. So obviously this is going to be the big R. It's going from 0 to the function 2x. So that's just 2x. And the little r is from the axis of rotation go to the inner edge. In that case, which is just x. And then put in the integral. Sum the big radius square minus the little radius square dx. The big radius will be from axis rotation to the outer edge of the function 2x. The inner function 0 to x. Right. This is also simple enough where we can do it by hand. Just leave pi there for a moment. 2x squared is 4x squared minus x squared dx. We can take the pi outside. 4x squared minus x squared is 3x squared dx. So it is going to be pi 3x squared. The integral is going to be x cubed over 3, going from 0 to 2. 3 and 3 cancel out. Pi x cubed 0 to 2. Put in 2 and put in 0. Just 8 pi. So a pi. Right. So that is the washer method. We have the outer radius and inner radius. So it is important that we think about this as the outer radius and the inner radius instead of the function of f like f of x or g of x. Because what we're going to do now is we're going to switch up and we do the dish and the washer method in the about the y-axis. And later on it will be complicated when the axis of rotation is it's not the x-axis or the y-axis, it's just any axis, vertical or horizontal. About the y-axis, sorry. Right. Now, I'm not going to write the formula like what they have here. It is a bit complicated. I just want to write like this instead. It's going to be volume. Some limits doesn't matter. But since we rotate about the y-axis, it is going to be dy. There's a pi here. And then we have the function r squared, but it has to be in the function of y minus r little r y squared. Sorry, that's bad. But again, the big radius square minus the little radius square in terms of y. Let's put the limit so it's correct. See it today. It's easy enough. And this method is the washer method, except there is no hollow region, so we have no inner r. But the function is in terms of y. So that's why I've tried to avoid writing f of x or g of x, or in this case p of x, p of y, and g of y like we have in the formula. They're too much to memorize. So bottom line is just going to write this. The volume for the washer method the volume equal to pi the big radius minus this little radius, and then could be either dx or dy or the width. The width is dx or dy. Dx is where we rotate about the x-axis or anything horizontal. Horizontal axis, like the x-axis. Dy is where we rotate the y around the y-axis, which is the vertical axis. Because later on it may not be the x-axis or the y-axis anymore. It is something horizontal or vertical. Anything horizontal, when we chop it up, it's going to be dx. Anything vertical, when we chop it up, it's going to be dy. Right. And if it is dx, we just have the function in terms of x square minus little term of x square. And if it's dy, let's put the limit a to b here, c to d. And if it is a function of y, will be the function of y square minus little r y square. So if it is dx, we use the function of x. If it is y, we use a function of y. And that's just that. And this method is kind of the same thing. Except we don't have the little r. And we have the width. I'm drawing the width because that could be either dx or dy. Right. Now we have a lot of examples. That is the script on. Now, so we're going to rotate on, but the first part we rotate about the x-axis. This is in the first quadrant, so we only need x and y, positive x and y axis. Two, 4, 6, 8. Right. This is x equal to y cubed, so it's not going to be the function, so we have to kind of just plot in the points, see what happens. So x equal to y cubed. Right. When y equal to 0, 0 cubed is 0. When y equal to 1, 1 cubed is 1. When y equal to 2, y cubed is 4. Right. So we're just going to plot. Sorry. 2 cubed is 8. Right, so we have those points. 0, 0, 1 and 1, 8 and 2. So kind of like that. And then x equal to 4y. Just try to sketch that as well. X equal to 4y. When x equal to 0, when y equal to 0, 4 times 0 is 0. When y equal to 1, I don't want to do that because, yeah, y equal to 1, 4 times 1 is 4. 2 is 8. So 0, 0, 4 and 1, 8 and 2. So when we graph this, we see the intersection 8 and 2 and 0 and 0. And 0, 0. Right. So the region is going to be this one, right? This is going to be the x-axis, horizontal. So it's going to be the x. And my question is, this the dish or the washer method? So when we look at this, when we rotate this about the x-axis, there will be the hollow region. Besides, I think it's always just set up the problem with the washer method. If it just happen to be no hollow region, then the little r in here set that equal to 0. So I think it's can just go with the washer method. The inner radius might be 0. And here we use about the x-axis, horizontal. So we just chop it, and each one we have is the dx. And the limit for x on here, the region go from 0 to 8. That's easy, right? Now we just need to determine the big radius and the little radius. The big radius is from the axis of rotation to the outer edge. So in that case, it is going to be that function, right? And I'm not going to write anything yet. And the little radius is from the axis rotation to the inner edge. The only problem here is it has to be in the function of x. So we have to write this in terms of function of x. This one is easier, so we go with this first. If x equal to 4y, then y is equal to x over 4. Remember, we have to write that as a function of x if we're going to use dx. Now, if x equal to y cubed, we can show for y it's going to be cube root of x. So now get back to this. The big radius from the axis of rotation to the outer edge. The outer edge, the function is cube root of x. The inner radius, the smaller radius, is go from the axis of rotation to the inner edge, which is x over 4. And put both that in the integral. So we have of v 0 to 8 pi cube root of x minus x over 4 dx. Right. Next we want to rotate the same thing, but this time about the y-axis. By the way, when we rotate about the x-axis and the y-axis, the volume will not be the same. May or may not be the same, but usually not, because we do not have the same volume. Think about this. If we rotate, we have kind of small one, but now we rotate about the y-axis, it's swing to the left and right. That's certainly different. But the region script R is going to be the same. Right, and just leave it like that. And then x equal to 4y remember there's a 0.2 and 8 here. I mean 8 and 2. Right. Now, this one is rotate about the y-axis. So if it rotate about the y-axis or any vertical axis, it's going to be dy. So we set up the integral with dy. So the vertical axis, if we're going to chop it, slide the axis, each increment is going to be dy, right? The vertical, so it's going to be dy. Right. For dy, And for this region, the y values go from 0 to 2, right? So the limit for y is 0 to 2. Now, big R square, and what is the big R? And what is the little r? So the big R is from the axis of rotation, the y-axis in this case. From the axis of rotation here, we go, the first h that we see is going to be y cubed. By the way, it is the function in terms of y, so it is perfectly to use y cubed. From the axis rotation, from the axis of rotation to y cubed, we see that one first. So this is, oh shoot, sorry. That is the little r, right? Because that is the inner edge. The inner edge from the axis rotation to the inner edge. So that's going to be y cubed. Now, the outer edge, from the axis of rotation, we go to the outer edge. Is this function. So the big radius is 4y. I don't know why I write like that. For y. Right? So, yeah, it's not any function in particular. We have to be able to draw it, the inner edge, and then the outer edge. Inner radius, outer radius, small radius, big radius. Bottom line is 0 to 2 pi. The big radius is 4y. The little radius is y cubed. Right. Now we just do the setting, the integral here. Right. Later on, we may rotate the region about any axis, like in this case we have rotate about the x equal to -1 or y equal to 2. So it's not the x-axis or the y-axis anymore, so we have to draw it in order to see. Bottom line is, if it is the vertical axis rotation and we chop it along it, it's going to be dy. If it is the horizontal axis, when we chop it, each increment is going to be dx. And the big radius square minus the little radius square. So that's how I set it up. I went over this part of the note very slowly because this is very important. This part, when you go to calculus 3, we have to be able to set up the region, draw it, and then set up the region. So that's why I'm going very slow here. We run out of time, so I have to stop here. We're going to pick it up. We're going to pick it up on Monday. So if you have any question, just send me an email. Other than that, have a good weekend. See you on Monday. So I'm going to end the stream here.